Hey, what's up, guys? This is Sheng here. So today, let's take a look at this 1255 maximum score words formed by letters. Okay, mm, it's a hard problem, but I think to me it's more like between medium and hard. I mean, regardless, let's take a look at this problem. Okay, given a list of words. Okay, so you're given like a list of words and then a list of single letters might be repeating. Okay, and the second parameters you're given is like the list of letters here. Okay, let me increase the font a little bit. Cool. So and okay, so and now the second parameters is a list of letters. You know, it could be duplicate. For example, this one we have two A's, one C, three D's, one G, and two O's. Okay. And then the third one, the third parameters is just like a score, basically, a score of every character. So you have a score of with a length of 26, right? For example, this one, right? It's a 26 length of of list representing the score for each of the letter, starting from A, B, C, D, and until the last one Z. Okay, and then and then it asks you to return the maximum score of any valid set of words formed by using the given letters. The words I cannot be used two or more times, which means each of the words can only be used once. And it asks you to return the maximum score that basically any combinations of these words. Okay, so it has to be the whole word, otherwise it doesn't make sense, right? And okay, and to be able to form those words here, you have to use the letters in this letters list here, right? And each of the letter can only be used once. So which means if you have used both of the two A's, if you wanna have another, if you wanna use another A to form the other words, you can't. Okay, cool. So and it asks you to return the maximum score to have any valid set of words. Okay, for example, this one, the first one. The first one is we have one A, sorry. So the score for A is 1, for C is 9. So so we have like that with a score of 11 and a good with score of basically that plus good give us like total score of 23, which is the highest score here. So okay, so now it's quite clear that this problem is like a combination problem, right? Basically, we just need to choose any of the combinations, right, between all those words here. And for calculating the combinations, we usually use the backtracking, right? You know, if you guys still remember, like you're given like a list of a different numbers, like 1, 2, 3, 3, 4, 5. Okay, basically it asks you to calculate all the combinations of those words, right? Basically, you have 1, 2, you have 1, 3. It's a different as a permutation, right? So it's a combination, right? It's not a permutation because permutation means that you have to use all five words, right? All five numbers in this case. But the combination is that you can choose from any number of those five numbers. In this case, it's like any number of words. Okay, so to calculate the combinations, we usually use a backtracking. Basically, for the backtrackings, the first parameter is always a starting point. We have a backtracking. Okay, backtracking, and the first element is always the start. It's a start index. Basically, it marks our starting point of the index in these words here. And the second one is, in our case, I think it's something like a current score, right? Okay. Yeah, basically that's the backtracking. And then other than that, so after the backtracking, it's just like how can we calculate the score here, right? Yep, I think that's the main idea here, right? Which yeah, let me try to start coding, and maybe I'll try to explain a little bit more here. Okay, cool. So like I said, first backtracking, okay, backtracking, backtrack, right? And then, like I said, the first one is start index, and um, second one is the oh, sorry. So for the second parameters, in this case, we don't need the score. Instead, we need what we need is the for each of the backtracking method, we need like updated versions of of this letter here. Okay, basically, at each of the backtracking method, we need to know how many letters left that we can use, right? Basically, we need to get an updated version of the letters. But if the letters here, if the letters is small, I think we can use like a bit mask to do that. But if we scroll down here, see the letters length is it's 100, which means we cannot use the bit mask. So basically we have to use like a dictionary or hash table, right? And to store that. Basically, here I'm I'm have like a letter counter, okay, here. So and yeah, so that's that. And every time, right, we just update, we just try to get a new word, and then we're trying to see, okay, if we can uh, if we can form that word with this letter counter. If we can, then we know, okay, that's a valid word, and we can just add that, right? And then we can just keep going. Cool. So then to start with, we have to do a counter, right? The of the letters, right? So that's like a Python's counter method. Basically, this will return like a hash table with the key of each of the letters and the value of the count of the appearances of that letter. Okay, cool. And so and here in the end, we simply call backtracking. Okay, and at the beginning it's 0 index, and the letter counter is this counter, right? So that's that. Cool. So for the backtracking, right? So for backtracking, and we have an answer equals to 0, and since we're getting the maximum numbers, right? I mean, we can simply return it in the end, so that we don't have to have a, like a or you know what, or you can also do this. You have a answer here at at the very top here. And here, besides the list letter counters here, you can also pass in like current score here, right? So that, I mean, later in the end here, when we reach the base case, we can simply use this current score to update this answer. That's one way of doing it. Okay, and another way is that we can simply let this recursion to help us to calculate that, and in the end, we simply return it. Okay, and the way I'm doing it is that, so I'm going to remove this part here. Okay, so basically for I in range start to to end. Okay, so we also need to define like the length of the words here, okay, so that we can loop it. Okay, so that's the end here, right? So and basically now we're looping through the words from the start index to the end. Okay, and the word is words dot I, right? So mm, uh, I'm going also to define like word score here equals to 0. Okay. Basically, what we're trying to do here, we have a for C in word, right? If C uh, in the letter counter, right, and the letter counter uh, uh, C e greater than zeros, then we know, okay, fine, we can so this ladder we find it and then we just decrease it by one, right? And then of course we have a word score plus, right, plus the what, the score, right? So the score of what, we need the index, but we have a ladder, so we just need to convert this ladder into the index based on letter A, right? So the way I'm doing it is we do a ordinal C minus ordinal of A. Okay, basically this will give me the index based on A here. For A is 0, for B is 1. That's how we get the current score for this ladder here. Okay, but there's an issue here, because and or because since we're doing a backtracking, right? So we need to, after we are doing this backtracking call, we have to change this, revert this ladder counter to its original value so that the next for loop will have the same starting point, right? But since we have this kind of like, since this is a dictionary, and depending on the words here, we have uh, it could be we only find part of the letters in this word. Okay, and later on it's gonna be a little bit trivial, not that trivial. It's gonna be a little bit uh no annoying to revert this thing back based on the current word. So to simplify these operations, the simplest way is, at least for me, is I'm just using a temp counters from the original counters. I do a deep copy, that deep copy of the letter. Okay, and here I'm only using this temp counter, right, to help me check that, and later, meanwhile uh, I'm also like updating the temp counter so that every time we'll always have a fresh start for each of the for loop here. Okay, so and and basically we have an if here. So if means that, okay, so we find it, but else, what happens for the else? Else means that, this letter cannot be satisfied, right? So we need to break it basically. So it means that we cannot choose this word. Okay, and to do that, I'm also using like a variables here to sig to to signal if we can actually use this word or not. I'm pretty sure there are some other ways you can do this logic, but at least for me, this is my first approach. I'm just using a bunch of variables that help me finish my logic. Okay, basically that's what I did here, right? So valid equals to false. Okay, so basically before breaking the for loop here, I set this valid the flag to false. So and here basically after this for loop here, if it's valid, then we do a DFS call, right? So answer equals the max of answer dot backtracking. Okay, here remember we do a I plus one, not the start not the start plus one. Okay, so this is at least I fell in this kind of like a pit several times. I was using the start plus one, and I was like, what happened? I've spent some time trying to debug it, but yeah, remember always do a I plus one because we are processing the current ice word, right? So that's that. And then here we just simply pass this temp counter, okay? Because this is the temp counter is the updated one. That's the ones this backtracking method will be using later on, okay? And of course we do a plus word score here. Okay, cool. So, and here in the end, we simply return this answer. Yeah, so that's that. Now the base case, right? So when do we stop? Basically, the if start equals to n, right? And then we return 0 in this case because we are getting the maximum, right, from this recursive call. So by the time we reach the last last words, or at this moment there's no more words left, so that we simply return 0. Cool. So yeah, as you guys can see here, basically for each of the words here, right, we're getting the maximum out of all the possible scenarios here, right? And then of course we have to plus our current word score, right? And then yeah, that's how we calculate the maximum score uh, with all the combinations. I'm gonna try to run the code here. So cool. So this one passed. Submit. Yep. So it's success. You know. So I think, like I said, there's another way of doing it. For example, like I said, since if we have answer here, right, answer equal to 0. I mean, if like I said, there another way of doing this. We can also pass in the current score here, right? So if we have a current score here, right, and then so here, I mean, if we do that, right, I mean, we don't need to do this max here in here, so we can simply do this. So if the start equals to n here, we simply do the answer equals to the max of answer dot current score, right? So and it means that we don't need to return here, right? Because we're handling everything, we're handling all the calculations to the end when we reach the the end, which when we reach the base case, okay? And then here basically there's no need to do a max here because we are doing the max in the end here. So we're just doing this backtracking here, backtracking call here, and of course we have we need to do a current score plus the word score, right? And here we're not returning here. We just call this backtracking method and we ask the backtracking to calculate that, and in the end we simply return the answer. Yeah, so we have a counter, and at the beginning it's 0. I'm assuming this should also work. Let's see if I'm right or not. Oh yeah, of course. So non-local, right answer. Okay, run the code. Hmm. Oh, return. So oh yeah, there's no point of defining our answer here. So and let's see, let's run the code one more time. Yep. So accept it, submit. Mm. Hmm. Yeah, it seems like the second approach doesn't work somehow. Hmm. I see. I think the reason being is this, you know, we shouldn't only update the answers while we're at the end because we might not we might not always be able to reach to the end because here, you know, if for some reason the word cannot be this current word cannot be formed somewhere in the middle, we simply just stop here because we only proceed when the current word can be satisfied, right? So which means that uh hmm, yeah, so which means every time, right? Every time we should do this. Yeah, and we just need to do this, right? So yeah, let me see if this works. Yeah, so now it works. Okay. Basically, we are so this base case is only for us to stop this for loop, right? And and then and then but when we are updating the answer here, so like before, how we update the answer, we for each of the loop here, we always compare it, right? So same thing for this second approach here. Basically, because like I said, I mean, it our loop, our backtracking could stop at any word, right? Basically, could we could have stopped at this word here because there's no other words that can allow us to form this good here. So that's why we have to every time, right? We have a new score here. We have to compare with the current answer. Cool. Yeah, I think that's it. And okay, let's see what else we have here. Maybe the time complexity, right? So, mm, so for the time complexity, right? Let's assuming we have n words, and so the total combinations of that, I think it's 2 to the power of n. No, the combination is this. So the combination is the is n times n minus 1 divided by 2. That's the combination, right? The total combinations of this length of n words. Am I right? Okay, let's see. No, I think the formula to calculate the combination is this. It's n factorials divided by k factorials of n minus k. But in this case, k could be from 1 to n, right? So, hmm, yeah, so I think in the end, it's still like 2 to the power of n of the total combinations. Yeah, and for each of the combinations, right? For each of the backtrack here, we have like we have a loop for the C here, right? Basically, I think for the let's see, we have M here. M is the average length of the letters here. Okay, so yeah, basically the time complexity for this one is 2 to the power of n times m. Yeah, that's the time complexity. And the space complexity, I think space is constant. I mean, I mean, besides the recursive call, right? Because here the counter here, the size of the counter is like 20, it's at most 26. Okay. Yeah. Yeah, I think that's should be correct. Hmm. Okay, cool guys. I think that's it for this problem. Thank you so much for watching this video, guys. Stay tuned. I'll be seeing you guys soon. Bye bye. Mhm.